water, pH, and emulsions. So now that we have a solid understanding of atoms and molecules, let's expand our sort of foundational knowledge and move specifically into food. So we'll see that there's four main components of food. There's water, there's proteins, there's carbs, and there's fat. We're going to spend a lot of time talking about each one of those components, and the first component that we're going to talk about is water. So we've seen water before. Water contains one oxygen atom and two hydrogen atoms that are bound together covalently. So we have a covalent bond, or a sharing of electrons between the hydrogen and the oxygen, which makes it very strong bond between those two. So it's not going to break up easily. We have to add a lot of energy to actually physically pull those two atoms apart. If we look at the actual molecule of water, represented here, we will see that it's got a bent shape. The two hydrogens are coming off at sort of an angle from the oxygen because of the presence of these unbonded electrons up there. Those are actually pushing those hydrogens down, so we get sort of this bent or angular arrangement, which we saw last time that this is going to be capable of hydrogen bonding. This separation, this large number of electrons on top versus the low number of electrons on the bottom, is going to be a separation of this charge, which will allow for a special interaction between the hydrogen and the oxygen of another water molecule, right? Which means that this really gives water some very special characteristics, right? If we look at liquid water, where these water molecules are sort of moving around freely, they're going to be able to because of the amount of energy that they have, this internal energy, they're going to be able to get fairly close. As that energy goes down, as it cools, we lose energy and we start looking to form a solid. Now, the arrangement is going to be such that those are going to prefer that the hydrogens on this oxygen are arranged in such a way that we'll actually see the water substance actually expand. When we form ice, ice is going to expand or have more volume than the liquid water. Which is why if you take a sealed container of water, stick it in the freezer, as it freezes, it can actually cause that container to burst. So if you take a soda, for example, stick it in the freezer because you want it to get cold quickly, forget about it, you come back in a couple of hours and that can is literally exploded. It's exploded because as that water freezes, it's allowing this to form a specific orientation because of the hydrogen bonding that's causing it to actually become more dense. Right? And this is very important because ice actually floats on water. It's more or less dense than the underlying water, so ice floats. Right? We can talk about a lot of reasons that is good, but we see it's one of the few substances where that is true, that the solid is less dense than the liquid. Right? Another thing that's important about water is it has a high specific heat. So it takes a lot of energy to change the temperature of a mole or a certain mass of water, right? Which makes it ideal for cooking. Right? So we'll see a large portion of the things that we do are somehow involved in, they're cooked in water. Right? We get a very, once we get that water to that temperature, there's a lot of energy stored there, which we can then transfer through this fairly inefficient system into other foods. Right? We can boil pasta, we can braise meat, we can fry things, although we don't usually fry in water. But because of this high specific heat, it plays an important role. And typically when we make things, one of the primary functions we do in cooking is actually get rid of water. Water will continuously leave food products, which is why it takes a lot of energy to cook. Because of this amount, it's going to take a lot of energy to move that water from the liquid stage into the gas stage so it can be removed from water. We can define the systems, the states of that water using this, which we refer to as a phase diagram. It talks about the pressure conditions versus temperature and what state that would be in. This is the phase or representation of the phase diagram of water. When we're at low temperatures over a wide range, we get ice, right? If we keep the pressure the same, so if we look here, if we go to a pressure of 1 atmosphere, which is typical normal atmospheric pressure at sea level, as we increase the temperature to 0 degrees Celsius, right, that is what we refer to as the melting point of water. Now ice is going to transition into water. Right? And it's going to take, if we looked at that, we're going to have to, what we're physically doing is breaking apart that interaction, that hydrogen bonding of the ice to let those water molecules become mobile, unattached. So when we get to that transition, we're going to have to add a large amount of energy to do that, to break all of those bonds. Right? Once we get into water, we can continue increasing the temperature until we get to 100 degrees Celsius, which is the boiling point of water. So typically we'll be jumping back and forth between these two temperature units. Celsius is sort of the standard scientific unit, which is based actually on this boiling point of water. This transition at 1 atmosphere is where that degrees Celsius has come from, where 0 is the freezing point or melting point, and 100 degrees is the boiling point. Typically, though, being in the US, we work more with the English unit of Fahrenheit. We know that the boiling or the melting point of water is actually 32 degrees Fahrenheit. The boiling point is 212 degrees Fahrenheit. So that Fahrenheit scale, interesting story, was supposed to be based on body temperature. So the normal body temperature we try to set at 100 degrees Fahrenheit, but unfortunately, for Fahrenheit, the subject that he chose to base all his measurements on was sick. He had tuberculosis, so he had to constantly had an elevated temperature. Suck. Which is why normal body temperature is actually 98.6. It's slightly lower than what he based it on. Science, sometimes you get screwed. Sorry. But again, this transition, the conversion is fairly simple between Celsius and Fahrenheit. Look it up on the internet. We're not going to go through it here. But we see that this occurs, right? So we're going to be typically water we're going to spend a lot of time dealing with because, again, it's a major component of food. It's in almost all types of food. It's one of the common cooking mediums. So we're going to have to understand this transition. Like I said, the other major components of food, proteins, fats, carbohydrates, we're going to spend a large amount of time talking about those individually. We'll come back to those another time. One of the important properties of water, the direct results of water, is what we call pH. It's the measure of this proton concentration. So we can talk about the pH as being the negative log of the amount or concentration of H plus, or a single proton. If we look at the hydrogen has 1 proton, 1 electron. We remove that electron to make it positive. All we have left then is this proton. So when we talk about an H plus, that is simply a naked proton. Those don't exist very well, so typically they're involved. They get swallowed up by another water molecule, and you might hear it be described as an H3O plus. It's a water molecule with an extra proton on it. Those two terms, the H plus and the H3O plus, are equal. They're synonymous, so we can look at those. Right? This presence, the pH present typically has a value of 1 to 14. Right? And the pH of a food is really going to have a direct impact on its flavor. One of the things that we can taste, one of the few properties that we can physically taste with our tongue, is the presence of pH, whether it's salt or sour or sweet or tart. Excuse me, sour or the presence of sour we can taste, which is going to be represented by having a high pH. So things that have a high pH or low pH, are very acidic, have a large amount of H+, we're going to recognize as having sour. Right? It's going to help us balance some of the sweetness we get out of the sugars and stuff later. So we'll always see that in order to get that balance, we'll try to lower the pH. So if we have a low pH, which corresponds to a high amount of H+, we're going to get a low number because of the nature of this calculation. Right? If we go, and that's the low pH we're going to call acids. A neutral pH is 7, which is really just pure water. Gives us to how much of that H2O is broken up into its H and OH. It has a value of 7. If we go higher pH, which means we're having low amounts of H+, we get to refer to as basic. And we're going to see that food falls all within this range. The text has a nice example, a list of different foods and where they fall, what their pH values are. But really the pH is going to have play a large role. It's going to help when we talk about food preservation. The underlying pH of the food is going to affect how we do it. The flavors that we have to balance out some of that sweetness. If we have a high sugar concentration, we will lower the pH to balance out that with some sour. The lower pH is also going to help us start breaking stuff down. So if you look at stomach acid, how we digest food, it actually has a very low pH. It's about 1.3, right? So pH is going to play a very important role. It also will help if we lower the pH. If we have very acidic foods, it's also going to do what we call denature proteins and interact with their structure, which is going to help us cook things. We can cook food by adding strong acids or strongerish acids to actually denature that and start the cooking process. We will see that when we make cheese, for example, we're going to take advantage of this denaturing, and we're going to add milk, and the milk fats and proteins we're going to hit with pH, low pH, and that's going to help start this curdling process where we actually get curds, which makes yummy cheese. So again, pH is going to play a pivotal role in our understanding of food and cooking. The last sort of concept for this one, we're going to start talking about structures of food. And interestingly enough, we're going to revisit these emulsions and foams throughout the course. Right? One of the last things we're going to talk about is sauces, which rely heavily on these emulsions and foams. But we wanted to introduce them here as sort of a basic structure. And these emulsions and foams rely on the fact that not all all molecules are going to interact well. Some things like water, which are capable of having hydrogen bonding, are going to interact well with other things that can do hydrogen bonding. Things like oil, very nonpolar, relies heavily on interactions, the van der Waals interactions. Those two things aren't going to be able to mix. Right? They don't like each other. They're frenemies, if you will. They don't really want to interact. We can cause them to interact through this idea of emulsions. So a classic example of emulsion is something that's like oil and water. We make a salad dressing, for example, if you choose to do that lab. We're taking oil and mixing it with vinegar, which is primarily a water-based acid. And we can actually get those two to interact. So an emulsion is a combination of oil and water. They don't interact completely. What we do is we make one of them very small particles and sort of distribute them evenly through the other one. Right? So if you look at salad dressing, when you take the oil and water and you shake it, you get that very cloudy mixture, which we call an emulsion, where the oil actually breaks into very small bubbles and will be distributed out through our water mixture. We could also have emulsions that the other way, where we take water, make very small bubbles of it, and distribute it through the oil. Both are possible, but really it's the things that like each other, like the oil is going to try to hang out with the oil, and we're going to sort of isolate that in this large solution of water, or vice versa. A foam is similar, where we're taking things that we're creating bubbles or small sort of isolated things, but the bubble is going to be air. So when we make a foam, we're going to talk about trapping air inside this other liquid thing, and that could be water, that could be oil, it could be a combination of the two. We can talk about foams being present. If you make, I'm trying to think of foam. Whipped cream, for example, is a foam. The head on beer, a foam. You're probably fairly familiar with foams, where we're trapping air bubbles in this other mixture, and we're gonna sort of take advantage of that to get light and fluffy cakes. For example, we're gonna try to make a foam inside, where we're trapping air bubbles in this sort of batter mixture. That batter then is going to transition from a liquid to a solid, and we're going to sort of permanently have those bubbles, and we get a light, airy sort of bread or cake. To help these sort of emulsions or foams become stable, especially in the emulsions, we're going to use what we call emulsifiers. And these are molecules that are going to have two different types of possible interactions. One side is going to be polar. It's going to be able to interact with the hydrogen bonding of that water, that polar thing. So it's going to be, this side of the molecule is going to allow us to interact with the water. This side of the molecule is going to be nonpolar. It's going to only be able to interact versus van der Waals, which means that this side is going to interact with the oil. So now we're going to have sort of a bridging molecule. That this side of the emulsifier can interact with the oil. The other side can interact with that outer water. So that actually will stabilize this bubble and not allow them as easily to separate, and will become fairly stable. We're going to see that one of the first things we do in lab is actually look at this by making, it's one of the first few, making either mayonnaise or salad dressing, where we're going to be making these emulsions. One of them is going to be highly stable because of the presence of emulsifiers. The other one is not. It's going to separate fairly quickly. I'll let you discover which is which based on this understanding. Again, water is a critical component, one of the major components. We're going to talk about the phase transitions of water over and over again as we talk about cooking. We're going to continue to look at the pH by looking at its effects. Just want to give you a basic understanding here and an introduction to emulsions and foams.